Hello, everyone. Welcome to the another lecture of synchronization. So in this lecture, we'll be looking at another problem of synchronization, which is dining philosophers problems. And then we'll be looking at another form of interprocess communication, which is through messages. And finally, we'll understand how to design data structures such that we don't need synchronization at all. So first, let's look at another synchronization problem, which is one of the famous synchronization problems, which is dining philosopher problem. So here, as the name suggests, there are philosophers. Specifically in the basic setting, there are 5 philosophers, and philosophers just eat and think. And there are 5 forks on the table. And each philosopher needs 2 forks to eat, and they can pick one fork, only one fork at a time. Okay. So here the goal is we want to generate a policy. Rather, we want to create code for each philosophers so that they all can follow this code so that everyone can eat. Okay. Because all the philosophers are hungry, we want to make sure that everyone uh, will get to eat eventually. And furthermore, we also want our policy to be fair, so such that none of the philosophers get starved. Okay. So what's the basic policy? Like the basic policy of philosophers can be as shown on the slide. So here, the philosophers, each philosopher can be modeled as this a simple while loop where they think for some time and they try to get forks. And then once they succeed getting forks, they eat and then they put the forks back. And this process continues. Okay. And to help our task, we can create like 2 simple helper functions. Left, which will return left fork, which will basically return the index for the left fork, and right, which will return index for the right fork. And since we can consider each fork as a resource, we can create a binary semaphore for each of the forks. Okay, so this is our basic setting. Okay. So, like, what can go wrong in this simple code? Let's say we write this, let's say we consider this policy without using any logs. Like, what can go wrong here? So, there are 3 things that can go wrong, at least 3 things. The first one is starvation. So, this policy can leave some philosophers hungry forever. In the sense, a philosopher may not get to eat, may not get to eat for long time, or he may not get to eat, he may never get to eat. The other problem is deadlock, in which the philosophers are stuck so that nobody can do anything. Basically, they can be holding lock which are mutually dependent on each other, so they cannot do anything. The other interesting scenario is live lock, where the philosophers are constantly doing work, but they are not making any progress at all. Okay. So there are 3 conditions. There are 3 things that can go wrong. So okay, we mentioned actually in the previous lectures, we actually mentioned starvation and deadlock a few times, but let's see like what we mean exactly by starvation. Okay? So starvation here means a thread is waiting indefinitely. Basically, a thread is not progressing at all. Okay, and starvation can be can happen for one thread or more threads also. Okay. For instance, an example is, yeah, a low priority thread is waiting for resource which are constantly held by high priority threads. In which case, the low priority thread will never get to run. So low priority thread is actually starved, right? And deadlock is a particular case of starvation in which all the threads are blocked. None of the threads can make any progress. So here, an example of deadlock is as shown on the slide. Here, thread A, uh, it, 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 it has resource 1, but it is waiting for resource 2. whereas thread B has resource 2, but it has resource 1. So we can see a cyclic dependency of resources, which causes thread A and thread B to be just stuck. They cannot make any progress. They are not doing any work. So this situation is called deadlock. An interesting thing is, what is the relation between deadlock and starvation? Does starvation imply deadlock? No, right? Because we can have starvation without deadlock. As I mentioned before, so here starvation can happen only for one thread, like low priority thread is just waiting for resource. Okay? But that's not deadlock because not all the processes are waiting, right? But deadlock implies starvation. Why? Because when deadlock happens, all the processes are starved because they are stuck waiting for some resource. So deadlock implies starvation, but not the other way around. So another thing that can go wrong is live lock. So live lock is a situation where processes are actually doing something, but they're not making any progress whatsoever. Okay? An example is as shown on the slide. So here there are two processes, process A and process B, and we have two locks, lock 1 and lock 2, L1 and L2. So let's assume that we have a function called is acquired, which checks whether that particular lock is acquired by other process or not. Okay. So process A, what it is doing is uh, for process A and process B, in order to successfully continue execution, they need to acquire both lock 1 and lock 2. Okay. However, in order to avoid deadlocks, what we try to do is we try to acquire the locks in reverse order. So process A acquires lock L1 first and then L2, whereas process B acquires L2 first and then L1. Okay. And then we have a while loop which tries to give other process a chance to proceed. Okay. So basically process A sees that, hey, is L2 acquired? If L2 is acquired, then process A releases L1 so that process B can continue. Then it sleeps and then it acquires L1. And it continues this while loop until L2 is acquired. Okay. Similarly, process B does the same, but here L1 and L2 are reversed. So you can see that both processes could get stuck in this loop forever. Like they can alternatively acquire and release L1 and L2, and they can be spending time in this loop forever. Basically, they're doing work, but they're not making any progress whatsoever because they're stuck in this loop. So this situation is called live lock. Okay. Note that in live lock, processes are actually doing work, whereas in deadlock, processes are just stuck without doing any work whatsoever. Okay, now let's get back to our dining philosopher's problem. So a simple method for get force and put force could be, as we know, we have five semaphores, one for each fork. So get force method could be as simple as shown on the slide. Here we have two methods where we first try to get left fork, and then basically each philosopher tries to get left fork and then right fork, and the get fork succeeds when we get both the forks. Similarly, put fork, we put the left fork first and then right fork. Okay, what can go wrong here? Deadlocks, right? Because imagine if all the philosophers they picked the left fork. Okay, and then when they try to pick the left fork, they are just waiting for the right fork, because right fork is now taken by the philosophers who is on the right. So we can have a deadlock in this situation. So this is not a correct solution. So there are many possible solutions for dining philosopher's problem. One of the solution is proposed by Dijkstra. Here, what Dijkstra does is, so we follow the same logic, but except for the last philosopher, we kind of change the order of picking the fork. Okay. So if the fourth philosopher, instead of picking the left fork first, uh, that philosopher picks the right fork first. That way, fourth philosopher, like rather fifth philosopher, gives a chance for the previous philosophers to have an opportunity to pick the right fork. So basically, the picking of the fork is reversed for one philosopher. This kind of ensures that there is no deadlock. Okay, and there are other ways in which we can solve dining philosophers problems, right? We can just make we can just not allow five philosophers. We can only allow four philosophers, and then we can have odd philosophers and even philosophers changing the order of picking the fork. And we can have a token. Whenever somebody gets the token, that's the token indicates the ownership. So when some philosopher gets the token, he or she can pick both the forks. That's another solution. And we can have another solution where we see that if one of the fork is already picked, then don't wait. So there are many other solutions for dining philosophers problems. Yeah, it's I mean, I strongly suggest you to think of some solution that you think would provide all the properties. And when you come up with the solution, try to write the solution and see and try to run it for a certain number of times and see some properties of your solution, like fairness. Does all the philosophers get a chance to eat before one philosopher is eating twice? Okay, and is a philosopher getting less chances to eat, like starvation, right? And can deadlock happen, right? So try to I mean, you can use either Dijkstra solution or you can write your own solution and run it for like 100 times and then see from the output you can do some analysis to figure out some properties of your solution. So we have looked at various concurrency problems. Specifically, we started with the milk problem, and we looked at producer consumer problem, readers and writers problem, and now today dining philosophers problem. So one thing that's common across all concurrency problems is that we need to allocate several resources among various processes such that the processes should not be deadlocked, and also there should be no starvation among the processes. Okay, so you can see this has a common theme among all the concurrency problems that you can ever encounter in operating systems. Okay, there will be certain shared resources, and that should be shared among multiple processes. And we need to make sure that the processes don't deadlock and they don't starve. So good. So we looked at various synchronization problems. Now let's try to understand other forms of interprocess communication without using shared data. So all the interprocess communication that we have seen, uh, like in previous two classes, are using shared data, right? So there is certain shared data where the processes have to access it or read or write to the shared data. Today, we'll be looking at interprocess communication without using shared data. So here, the communication happens with messages. So, in message passing, like in interprocess communication with messages, so message will be passed by one process and it will be received by another process, right? At any given time, the data is owned by either the sender or the receiver. Okay, and it cannot be owned by both the processes at a time. I mean, think about regular postal service. So the package, once it is sent by the uh, sender doesn't own the package anymore. Okay, and then eventually the receiver who owns the package. So at any given time, either the sender has the package or the receiver has the package. Similarly, so either the sender owns the data or the receiver owns the data in case of message passing systems. So, so the process, so at a very, very high level, so we can see that there is a process that is sending the message. We call that process sender. And there is a process which is receiving the message. We call the process receiver. And why use messages, right? Because messages are actually very natural when we think about communication between two entities. So humans, as humans, we actually use messages a lot. uh, like the way we communicate is through messages most of the times, right? And also messages allows communication between two different address spaces. Like messages want doesn't require the address space to be shared. That gives them flexibility. For instance, we can have messages pass between processes that are not running on the same system, because they don't need to have shared address spaces, right? and and they are less prone. That's the common belief, but that's not necessarily true. We'll be looking in next class how even message passing systems can have bugs. And and the code of the process, like, so here in case of communication through shared memory, you can see that the code for sender and receiver should almost be the same. Like when we are accessing some certain shared variable, the critical section should be almost same, right? So we should have same code. Whereas that's not the constraint in case of message passing systems. So the code for the receiver and sender could be completely different. Okay, because the only thing that they should have common is the send call and the receive call in the receiver and send call in the sender. The rest of the code could be different. We don't care. And unlike shared memory, where one process can have uh, some some control of the other process, in case of message passing systems, a process need not trust other process, because since the message would be received, since there is nothing shared between the sender and receiver, they need not trust each other, right? So so at very high level, you can imagine that message passing systems have two methods called send and receive. Okay, so send, it takes two arguments, mailbox and a message. So mailbox is basically a buffer where all the messages, all the sent messages will be stored. And receive also receives tries to read a message from the given mailbox. Okay, and then message could be either fixed size message or variable size message, where the size will be specified in the message itself, right? So, and the mailbox is actually interesting because depending on how the buffering is happening, so there are multiple ways in which send and receive could be implemented. Okay, like what are the possible ways in which send can be implemented? So it can be fully synchronous, in which case the send function will not return until the data that is sent is actually received by the receiving process. Okay, so this we call fully synchronous. So when we call send, so when the send function returns, we can be sure that the data that we sent is actually read or received by the uh, destination process. Okay, that is fully synchronous. Or send can be synchronous, in which case send will return once the data is received by the mailbox. It doesn't wait till the process reads the message. Rather, we just want to ensure that the message is saved in the mailbox. Okay, and when can synchronous be blocked? It will be blocked if the buffer is full, right? So when send returns in case of synchronous, uh, in case of synchronous mechanism, we can be sure that the message is saved in the mailbox. Okay, and if the buffer is full, in case of synchronous send, the send will be blocked because the message is not saved in the mailbox. And finally, we can have asynchronous send. So here, the send call will return immediately. Okay, so it is the moment we call send, we immediately return from send without, it never blocks. Okay, and this adds additional complexity to the sender, because now sender needs to check the status of the message that is being sent. So it is the responsibility of the sender to make sure that the message actually that was sent is like either is in the mailbox, or it's in the uh, or it's actually read by the receiver, so on and so forth. So operating system actually provides certain methods for asynchronous sends and asynchronous receives, so that you can ask operating system to signal you when the message is received by the receiving process. So instead of using fully synchronous, you can use asynchronous and tell the operating system to to inform you when the message is received by the receiver, or when the message is actually saved in the mailbox, for instance. That is asynchronous. So what about receive? So receive can be implemented either either synchronously or asynchronously. So here, in case of synchronous receive, so we wait till the till we receive some data. We wait till we receive some message. Okay. In case of if there is a mailbox and if the mailbox is empty, this synchronous receive will be blocked, because it ensures that there is some message that it can receive. Okay. In case of asynchronous receive returns immediately. It either gets the data from the mailbox if there is a message. If not, it will return back with a status code or return code or error code to indicate that there are no messages. Okay. So that way, if we really want to wait for the message, we can use synchronous message. Or if we don't care whether we receive a message or not, then we can use asynchronous mechanism. So what are the things that operating system has to take care while implementing these message passing systems or message passing APIs? So let's assume that sender and receiver are on the same machine. So when we want to have buffering, there are two choices. So either operating system can provide no buffer, or it can provide a buffer of certain fixed size. Okay. So in case of no buffer situation, the sender should wait till the receiver receives a message, right? So the send can be fully synchronous. It cannot be synchronous. It cannot be asynchronous. It has to be fully synchronous. Okay. And they synchronize on each message because there is no buffer. So when the message is sent, the sender cannot progress until the message is received by the receiver. Similarly, when the receiver tries to receive a message, it also cannot progress until the message is actually sent by the sender. That is the situation when there is no buffer, or when, let's say, operating system can provide buffer of finite size, in which case there are various mechanisms of send that are possible, like send can be fully synchronous or synchronous or asynchronous. So here, the only time when the sender will be blocked is when the buffer is full. So except for in the asynchronous case, right? So sender will be blocked only when the buffer is full, or else sender can just send a message and continue. Similarly, receiver will be blocked when the buffer is empty, or else receiver always receives a message if there is one in the mailbox in the buffer, and then continues. And then we need to use lock and condition variables to synchronize access to this buffer, because now the two processes are actually on the same machine. So in order to access the buffer, we need to use lock or like condition variable to make sure that only one process is actually accessing the buffer. So, and apart from buffer, what about links, like communication links between two processes? So when we have like irrespective of whether we have buffers or not, the communication can happen in two ways. The one is direct communication, okay, where we have the sender and receiver actually naming the process from which they are trying to send or receive the message from. Okay. So there is a communication link. There is a direct communication link set up between between two processes. Okay, and this communication link is exactly it's shared by only two processes, and there is only one link that is associated with any two processes. So this is called direct communication. So here, in case of direct communication, sender actually names the process to which it is trying to send the message. Okay. So here P is trying to send a message to Q, and similarly, receive method, uh, the process which is receiving the message, should also name the target process from which it should receive the message from. Right. So Q is receiving a message Q from process P. So Q is explicitly naming process P as a sender, and it wants to receive a message from P. So this is called direct communication, in which there is a communication link. There is a unique communication link established between pair of communicating processes. Okay. Now, what is the other form of communication? Like indirect communication, right? So this is an example of message passing system in case of uh, direct communication, where the sender, like let's assume producer is a sender, so producer is actually sending to the consumer an item. Once the item is produced, sender actually names the consumer to which the item should be sent. Similarly, consumer, it tries to receive an item by naming the producer. So consumer actually should know the producer from which the item should be received. Okay. So the other form of communication is indirect communication. So here, instead of um, directly naming the process, we use mailboxes or ports. So if you have taken network course, you must be aware of ports on systems, right? So these ports allow many to many communications, right? So mailbox, we can consider mailbox as a buffer, and so processes can send message to the mailbox and then receive message from the mailbox. And a link is set up among processes only if they can access the mailbox. So the link is set up through the mailbox. If the mailbox cannot be accessed, then the link cannot be established. Okay, and the link can be established between multiple processes, because the only condition is whether the process can access the mailbox or not. So if multiple processes can access a mailbox, of course the link can be established between multiple processes here. Note that there is no link per se, because we never name uh, the link is established only through the mailbox. So all processes, they send or receive through this mailbox, right? And this mailbox is usually owned by the operating system, and most of the times it requires explicit open and close calls to open the mailbox and close the mailbox. And then before send and receive, we should explicitly open the mailbox. So an example is as shown on the slide. So here process P opens the mailbox, then it sends a message to the mailbox and eventually closes the mailbox. Similarly, the receiver, process Q, also opens the mailbox. Here it receives it receives a message from the mailbox, then closes the mailbox. So there are some considerations that we need to uh, think in indirect communication. Here, uh, here in case of indirect communication, we have explicit requirement of mailbox. So the question is, where should be the buffer be, or like where should be the mailbox? Okay, and what are the where should be the mutexes or the logs that are controlling access to the mailbox be stored? So here, I mean, a simple example of mailbox is similar to the producer and consumer problem that we have seen before. So you can assume mailbox as a buffer with fixed size, and it's a FIFO, means first in first out the access to the buffer is in first out order, and most of the times the buffer could have variable size messages. So here, multiple producers or senders put data into the buffer, and multiple consumers or the processes that are receiving the data will receive uh, data from this mailbox. And then, and the only time when the producer block is or a sender is blocked is when the buffer is full. Similarly, only time when the receiver is blocked is when the buffer is empty. So there are various other issues related to the mailboxes, like it can be synchronous or asynchronous. It depends on the processes, because now we have buffer. So sender can either wait or sender need not wait. And also links, how are links established, and how can we be sure that the message is actually received by the target process. And when we have mailbox between multiple processes, how can we send the message to only one particular process? Imagine if the mailbox is shared by 3 different receivers, then how can a sender send a message to only one receiver, right? And also, can mailbox be directional or bidirectional? Like, can a producer act as both producer and consumer? Or like, does mailboxes in the mailboxes, can we actually have a direct connection by, basically we can have a buffer, we can send a message by having the destination receiver in the message itself, so that we can kind of mimic a direct connection. So there are many issues related to the mailboxes, right? And one of the interesting issues is exceptions. Like, what happens when process terminates? What happens when the sending process terminates? Or what happens when the message is lost? Because imagine if the processes that are communicating are across a network. Okay, so the message that is sent could be lost because because of network issues, or the process that sent the message could terminate. Similarly, the process that is supposed to receive a message could terminate. So what happens in these conditions? So when the message gets lost, like for when crossing a network, there are two approaches. One, like there are two things that we should do. We should have a mechanism to detect that the message is lost. Okay, and we should also have a way to retransmit the lost message. That way we can provide an assurance to the sender that once the message is sent, it's eventually be transmitted either through retransmissions or through single transmission, right? So we can provide an API for detection by acknowledging each message sent. Like when the message is actually received by the receiver can send an acknowledgement that gives an assurance that the message is not lost. Similarly, we can have a timeout on the sender. So when sender doesn't receive acknowledgement after within a given time, sender can assume that the message is lost. Okay. And these are the two possible ways in which we can detect a lost message. And once the detection happen, we can retransmit. We can either retransmit on timeout, like if we don't receive acknowledgement within certain time, we can just retransmit the message, or we can actually have sequence number for each message, so that we know which messages are not received. That way, the receiver can later ask the sender to send certain messages which are not received. Okay. And I mean, these are like the techniques here are similar to TCP. Like if you have studied TCP protocol, if you see the retransmission that is implemented by the receiver, this is exactly what happens. So TCP has sequence numbers for each messages. And then when the message is not received, usually receiver sends an acknowledgement with the messages that are not received, so that sender can send them again. So yeah, the other exception condition is process termination. Like the sender or the receiver could terminate while they are communicating. Okay. So let's say if sender terminates, In that case, receiver may be blocked forever, right? If receiver is using synchronous receive, if the sender is terminated, then the receiver is just waiting for the message to be received, but the sender is terminated. So receiver may be blocked. One way to handle this could be the receiver can periodically send pings once in a while to make sure that the sender is actually alive so that it doesn't wait indefinitely. What happens when the receiver terminates? So the same thing happens at the sender side as well, right? So sender can send the messages until, if there is a buffer, sender can send messages until the buffer is full. Once the buffer is full, sender will be blocked forever. And there is no, since the receiver is terminated, the messages will never be read. So sender is blocked indefinitely. So similarly, at the sender side, to avoid this, sender can periodically send pings to make sure that the destination receiver or the target receiver is actually alive. So which one is better? Like, is using shared data better or using messages better? Like, which one is the good way of interprocess communication, right? So, I mean, there is no right answer. Both methods are equally powerful, and both have its own pros and cons. Few times it's easier to debug message passing systems, whereas it's hard to debug shared concurrent programming using shared data. Few times, like, message passing systems could be easy when the processes that need to communicate around different machines, right? So in that case, message passing systems is more natural to think about. However, there is a distributed shared memory, the concept of distributed shared memory, where the memory is shared among multiple machines. Okay, so it was a hot topic back in 80s and 90s, but now it is coming back with all the shared data structures, with the cloud computing that we are using currently. The technique of distributed shared memory is coming back. But I mean, as an example of real world system, like if you have used map and reduce is an excellent example of message passing system, where you have mapper that is running on a machine that is computing some work, and mappers, when they finish all the work, they send the messages to receive to reducer, which actually coalesces all the results from each mapper. So however, there is also shared data used in various cloud computing machines. So we'll be looking at more about this in the next class. So, I mean, the correct answer is, we don't know. Correct answer, like which one is better, it depends. So it depends on the application that we are designing. It depends on the constraints on the application, and yeah. And also language support as well. For instance, few languages, like if you are using high level languages like Python, or Java, or other object oriented languages, it's more easier to think messages. Yeah. But if you're using low level languages, it's shared memory kind of comes natural. So it varies. So there is no correct answer. So the correct answer is, it depends. So as a last topic of this class, we'll be looking at wait-free synchronization. So we have seen that we solved various concurrency problems by using locks and various other synchronization constructs, right? Excuse me. So let's ask ourselves a question. So can we create data structures in such a way that these concurrency issues never happen? Like basically, And can we have a data structure so that it doesn't matter if multiple processes are accessing the data structure, there is no concurrency issue, and there is no busy waiting, and there is no possibility of deadlock? Can we create such a data structure? That will be amazing, right? If we can create our data structure in certain way, that way we never have to use locks whatsoever, and all the problems of deadlock will never happen. This is called wait-free synchronization. So here the goal is to design the data structures in certain way which allows safe concurrent access. And the design of data structure needs no mutual exclusion. Basically, all the operations on the data structures can be done without any mutual exclusion. And of course, if you are not using lock synchronization primitives like lock and semaphore, there is no possibility of deadlock as well. Here, the approach is we use a single atomic operation, and that will ensure that the state of the data structure is moved from one consistent state to the other consistent state. Okay, so there is no invalid state of the data structure. So any operations that we make onto the data structures are all consistent, irrespective of who makes it. So let's look at an example. I mean, this might make it clear to you. So if you have taken advanced C programming or data structure course, you must be aware of queues. So this is a simple queue, which is implemented as a singly linked list. So here, each node has 2 pointers, one next, which is pointing to the next element, and a pointer to an item, which is pointing to the item. Okay. So how do we insert an element at the head of the queue? Okay. So the simple way is we first have the new element. We make the next of the new element pointing to the head of the queue. And then finally, we make the queue pointing to the new element, right? So this is how we insert an element to the head of the queue. So the code for this is as shown on the slide. So here we first malloc an element, okay? And then we assign the item that we want to insert, and we make a new of next. We make the next pointer of the newly created node to queue, to point to the queue. And eventually we modify the queue to point to the newly created node because that is the new head. Okay. So here queue is the only shared variable among all the processes. Okay. So imagine if there are multiple processes that are trying to insert a node into the queue. Okay. The places where we need synchronization is as shown in blue color. So here, these are the 2 statements where we want to ensure that there are no synchronization issues, right? So how can we ensure that these 2 statements are actually safe? So I hope you all remember the test and set instruction that we studied in lecture 6. Basically, this provides us an atomic way to test test the given pointer, and then we can store a new value into the old pointer. Basically, the test and set instruction, it takes 2 parameters. The first one is a pointer, and the second one is the value. Okay. What test and set does is it reads the value from the old pointer, it reads the existing value, and it sets the value that is pointed by the given pointer. It will write new value to that pointer and it will return the old value. Okay. So this is called test and set. So let's say the processor have a test and set instruction. Okay. Now, how can we use this test and set to achieve synchronization between these 2 instructions? So it is as shown on the slide. So here, as you can see, we replace the last 2 statements with the test and set. So here we actually assign new of next to the queue. And whereas when we are modifying the queue, that means when we are actually writing to the queue, okay, we see that we try to write new, and we see that the value of queue is actually new of next. That means the value that we assign to the new of next is actually the one. Basically, we want to ensure that there are no processes that modify the value of q between when we set new of next and when we are changing the value of q. So this ensures that the two the two statements have happened. There is no other process that modified the state of q between these two statements. That is ensured by this while loop. And you can like, is this busy waiting? Actually, no, because each, like, when we are actually trying to write, uh, so it each the like at every iteration of the loop, it's just that only one process will eventually get an opportunity to do this. So basically we are ensuring progress in each loop. So this is not busy waiting. Yeah. So to understand this more, if you want to get a clear understanding, I strongly suggest you to write this code and try to have mental mapping of like try to have uh, multiple processes that are trying to insert an item into a queue, and think about what would happen when different processes try to insert the item. Okay, and you'll be surprised to see that it doesn't matter which order they execute, eventually we will end up in a very in correct state of the queue. So none of the items will be lost, and the queue will always point to the head of the linked list. Okay? Or the queue pointer will always point to the head of the linked list. So what are the limitations of wait-free synchronization? One is it works for simple data structures where the changes can be committed by one store instruction, because here um, so the way we are achieving synchronization is using this test and set, right? So if to make sure to ensure this, we need to have the constraint that we can only provide synchronization between one store instruction. If we have multiple store instructions, basically if we have multiple stores to share data, then it's hard to achieve wait-free synchronization. Okay, and what about complex data structures, like not singly linked list? If you have doubly linked list and where you have to do a lot more modifications, then it becomes hard to achieve wait-free synchronization. So more general approach, if you ever want to design data structures uh, that do not need explicit synchronization, the things that you need to remember is so so the operations should follow this simple pattern. So you should remember the current, let's say there is some shared data. Okay, you should remember the value of the uh, current data, and then you should modify, like you should store the value of the current data into some scratch location. You try to modify it. Okay, you try to modify the shared data by copying the old data, and you, whenever you're trying to modify the data, you always see that the modification has not changed uh, the old value of the data, because the one that you copied in step 2, you should ensure that in a loop the value that you are trying to copy, the old value of the master pointer to which you are trying to copy is same as the value that you have stored before. Okay, that way you ensure that no process has tried to write to the shared data. So in the next class, we'll be looking at more concurrency bugs, and we'll be exploring few techniques on how to find these concurrency bugs. Okay, thank you.